The study of waves is the province of physics. Much of what we know about the structure of atoms comes from the work of physicists. Therefore, before we can get entangled in the chemical implications of atomic structure, we have to familiarise ourselves with the physical basis of waves, light, and so forth. You are all familiar with waves: light waves, sound waves, radio waves, microwaves, etc. And all waves have the same components. We have a wavelength, they have a frequency, they have an amplitude, and they have a speed. For wavelength. Since waves are continuous, it is not possible to pinpoint a beginning or end. What we can do is identify identical points along a wave that allow us to determine wavelength and frequency. Thus, here is a wave. My artistic skills notwithstanding. The wave is moving in this direction, and we can identify crests or peaks and troughs. Wavelength then is the distance between identical points, i.e. from peak to peak, from here to here, constitutes one wavelength, or from trough to trough, from here to here, or any other point that is identified on the wave. In essence, any point along a wave can be used as the starting point for the purposes of determining the wavelength, but we use crests and troughs because those are easier to see. The unit used for wavelength is the meter. However, the meter is often modified by a Greek prefix that denotes either a larger or smaller amount than a meter. Examples of Greek prefixes that you will hear and use are giga, mega, kilo, centi, milli, and micro. Nano, pico, and femto. So if we were using meters, we could have gigameters, megameters, kilometers, centimeters, millimeters, micrometers, nanometers, picometers, and femtometers. In turn, each of these means times 10 to the 9 meters, times 10 to the 6 meters, times 10 to the 3 meters, times 10 to the minus 2 meters, times 10 to the minus 3 meters, times 10 to the minus 6 meters, times 10 to the minus 9 meters, times 10 to the minus 12 meters, and times 10 to the minus 15 meters. These Greek prefixes can be used with any other unit, for example seconds, grams, joules, etc. Frequency is the number of waves that pass a certain point in 1 second. The unit for frequency is thus waves per second. Usually we just write this as s to the minus 1 or hertz, and these have the same meaning. Thus, if a wave had a particular frequency of 10 waves per second, then we could write 10 s to the minus 1 or 10 hertz. Now speed. Waves can have a wide variety of speeds with units of meters per second or ms to the minus 1. So meters per second or ms to the minus 1. Sound waves have a speed of 330 meters per second. However, mostly we will be concerned with electromagnetic waves which travel at the speed of light. The speed of light is given the symbol c, and the speed of light is 2.998 times 10 to the 8, big number, meters per second. Now amplitude. The amplitude of a wave is the height of a peak. Simply put, it looks like this. From there to there is your amplitude. The amplitude is a measure of the intensity of a wave. The larger the amplitude, the more intense is the wave. Mentioned a few moments ago were electromagnetic waves. Light waves that we can see constitute only a small part of the electromagnetic spectrum, which is shown here. You will notice the different wavelengths and frequencies of these waves, most of which have familiar names. As you would expect, the wavelength, frequency and speed are related mathematically, and that is what we turn to now. The basic equations relating wavelength, frequency and speed can be summarized in the following diagram, where we have speed, wavelength and frequency. If we wish to find out an unknown, for example wavelength, we could cover up wavelength with our finger on this triangle and just write whatever is left. So in this case, wavelength, which has the symbol, Greek symbol lambda, this is lambda, and this is equal to the speed divided by the frequency. The frequency which is given this Greek letter nu, and it looks like a squiggly V, is therefore equal to speed over wavelength. And finally, if we wish to calculate the speed, then speed would simply be wavelength, forgot the L, sorry, and a whole bunch of other letters, times frequency. I can spell, I know how to spell wavelength. I showed you up here and I'll do it again. There's wavelength, look at that. I can spell. Good for me. So since we are concerned with electromagnetic radiation, the speed is the speed of light and it has the symbol c, and that's what we will use most of the time. In a separate presentation, we will look at a couple of examples of calculations that involve these equations.